Our next presenter is Kallio, and they will be talking about the properties of and effects on the near lunar surface, plasma, electric and magnetic fields, and charged dust.
Thank you. Yeah, so hello everybody. So my name is Kallio, and in this presentation I will discuss about the lunar plasma dust and electromagnetic field environments and different ways of how those regions can be investigated, and especially with the computer simulations. So the way how I will okay, yes, so I will start. So I'd like to demonstrate that there are many physical processes at different space scales and therefore also different time scales, which can affect human beings and man-made devices around the moon and also as on the surface of the moon. And the way how these issues are addressed in this brief review presentation is to divide the space around the moon into 3 different space scales. So we call those space scales as a macro scale, where the size of the investigation region is over about 1,000 kilometers. The mesoscale from order of kilometers to 1,000 kilometers or so. And finally, the microscale, where the investigated size is less than about order of a kilometer. And then we will go through those space regions in such a way that I will introduce very, very briefly how those regions can be investigated with different simulation approaches. But I don't want that we forget possibilities that the laboratory measurements can provide, and then finally some concluding remarks. Okay, okay, maybe this one. So first, space scale is the large scale, micro scale, which contains the whole moon and the space around it. We need to understand properties and the processes in this space region when we have a lunar orbiter or also a lander that stays a while in this space region. A good tool to investigate the space scale in 3D is a so-called hybrid model, where ions are modeled as particles while electrons form a massless charged neutralizing fluid. In this hybrid model simulation, we see the moon in the undisturbed solar wind, and the color shows the density of the solar wind, which is low in the wake region. But the moon is not always in the solar wind because it is about 1/3 of its time downstream of the bow shock. And it faces the bow shock is in the magnetosheet and in the magnetotail. This also means that we need a global model to simulate large regions of the Earth magnetosphere. Now I would like to point out one interesting consequence of this fact related to the properties of the solar wind particles which hit, so precipitate, to the lunar surface. I'm now using a simulation model that includes both kinetic and magnetohydrodynamic effects. So in this plot, red lines show constant, where is my mouse? Oops. Constant solar wind precipitation flux contours in percents from the maximum flux collected during one full orbit around the Earth in an imaginary situation when the Earth and its magnetosphere doesn't affect the solar wind. The highest precipitation can be found here at the equator, and the flux decrease when we move closer to poles. But here we see a more real situation. So now we also have the magnetosphere and the bow shock. And in this plot, we see the particle flux connected along the orbit, where the moon was in the undisturbed solar wind. There, The maximum is on the far side. Then when the moon is downstream of the bow shock and in the Earth magnetosphere, the maximum flux is on the near side. But here the plasma is disturbed because of the Earth magnetosphere and therefore the accumulated total particle flux and also other properties of the particle flux around the full orbit are not the same as they would be without the Earth magnetosphere. Now we zoom into the mesoscale and look probably the most interesting region in the space region, namely a magnetic anomaly. The space scale is now only a few tens of kilometers, and our example is Gerasimovich anomaly. Once again, we use the same hybrid model as in the microscale. Here the color map shows the total magnetic field on the lunar surface, and the green lines show the magnetic field lines. And the notable feature in this solution is that there is some kind of a mini magnetosphere around the anomaly. And it should be noted that in reality, the plasma magnetic field above the magnetic anomaly form much more complicated patterns than what we can see in this simulation, because as mentioned before, an anomaly faces many different kind of plasma and magnetic field situation during its full orbit. And now finally we will zoom even more into the kilometer and smaller space scales. And the most interesting region in this microscale is near a surface region. And in order to include relevant physics to investigate charged particles, especially charged dust particles, we have to use a full kinetic, thank you, a model where also electrons are modeled as particles. And next we will see an example calculated from a so-called electrostatic model where the magnetic field doesn't have time dependence. And here we can see several landscape, and the color shows the electric potential near different lunar landscapes. And we know the electric potential, we can calculate the electric field, and we investigate, for example, how charged lunar dust particles are behaving if they are injected at a certain place from the lunar surface, for example, from this point. Finally, a reminder that we can increase our knowledge, for example, about lunar dust environment also by taking laboratory measurements. And we have designed and built our own device to investigate effects of the lunar dust. And in this CAD drawing, okay, our vacuum chamber includes UV lamp, electron source, and camera. And here we see the device, a photograph of device where two faces are opened. And this device makes it possible to investigate, for example, how the dust affects different mechanical structures and how dust can be removed. As a concluding remark, we can say that the moon is a challenging place because it faces different plasma regions during its orbit. There is a direct plasma surface interaction, surface charging different particle species, especially dust particles. So there are many processes taking place in different time and space scales, and but we have different tools to investigate those even in the ground, especially computer simulations and laboratory measurements. So thank you for your attention. Once again, I apologize for the technical difficulties in the starting, and thank you for the help to solve it.
No worries, and thank you. That was a great presentation.